In September 2023, the James Webb Space Telescope detected methane and carbon dioxide in the atmosphere of a planet 124 light-years away. That alone was historic, but then a deeper analysis published in 2025 revealed something that changed the entire conversation. The planet likely has a water-rich interior. The planet is called K2-18b, and it's forcing scientists to rethink what a habitable world can look like.
A water-rich interior? Are we talking about an ocean?
Potentially. K2-18b sits in a strange category that doesn't exist in our solar system. It's about 8.6 times the mass of Earth and 2.6 times Earth's radius. That makes it too big to be a rocky planet like Earth, but too small to be a gas giant like Neptune. Scientists call these sub-Neptunes, and they're actually the most common type of planet in our galaxy. We just don't have one nearby to study.
The most common type of planet, and we don't have a single example in our own solar system.
Not one. Which is why K2-18b is so valuable. It orbits in the habitable zone of its star, a red dwarf called K2-18, meaning it receives enough energy that liquid water could exist on its surface. The JWST observations detected methane and carbon dioxide in its atmosphere but found very little ammonia. That chemical signature is significant
Why does the absence of ammonia matter?
because it's consistent with a specific theoretical model called a Hycean world. Hycean is a portmanteau of hydrogen and ocean. The idea is a planet with a thick hydrogen-rich atmosphere sitting on top of a global liquid water ocean with a rocky core beneath that. In this scenario, chemical reactions between the ocean and atmosphere would deplete ammonia, which is what the data shows. A July 2025 paper on ArcSiv used 4 additional JWST transit observations combined with the original data to confirm the water-rich interior interpretation. The team applied Bayesian analysis and found that the atmospheric composition strongly favors a scenario where K2-18b has substantial amounts of water, either as a deep ocean or distributed throughout its interior.
But I've seen headlines calling this a potential sign of life. Is that a stretch?
Here's where it gets controversial. The initial 2023 JWST analysis reported a tentative detection of dimethyl sulfide, or DMs. On Earth, DMs is produced almost exclusively by marine phytoplankton. It's the compound that gives the ocean its characteristic smell. If confirmed on K2-18b, it would be hard to explain without biological activity.
That's a massive if.
It is, and the scientific community has pushed back. A 2024 paper in the Astrophysical Journal Letters argued that the JWST observations of K2-18b can be explained by a gas-rich mini-Neptune with no habitable surface at all. Under this model, the planet is more like a warm, small gas ball than an ocean world. The atmospheric chemistry that looks like habitability markers could just be the natural result of high-pressure hydrogen chemistry.
So the same data supports two completely different conclusions?
That's the honest state of the science right now. It's not that anyone is wrong. The data from JWST, while incredible, sits at the edge of the telescope's detection capabilities for this type of analysis. An August 2025 report from NASA described the situation as 3 independent teams analyzing the same expanded dataset and reaching partially overlapping but distinct conclusions.
Is K2-18b the only planet where JWST has found interesting atmospheric chemistry?
Not at all. Another fascinating target is 2I-270d, a temperate sub-Neptune about 73 light-years away. JWST detected methane, carbon dioxide, and water vapor in its atmosphere. Like K2-18b, multiple models can explain the observations, and the debate about whether it's a mini-Neptune or a Hycean world is ongoing.
What made JWST capable of doing this when previous telescopes couldn't?
Spectroscopy. When an exoplanet transits in front of its host star, a tiny fraction of the starlight passes through the planet's atmosphere before reaching us. Different molecules absorb different wavelengths of light. JWST's infrared instruments are sensitive enough to detect these absorption signatures in the filtered starlight, essentially reading the chemical fingerprint of an atmosphere from over 100 light-years away.
The light passes through the atmosphere and carries information about what's in it. That's almost like reading a barcode.
That's a good way to think about it. Each molecule has a unique barcode. Water absorbs at certain infrared wavelengths, methane at others, carbon dioxide at others. JWST reads those barcodes with enough precision to tell you not just what's there, but roughly how much of it there is.
How many exoplanets has JWST analyzed this way so far?
JWST has characterized the atmospheres of dozens of exoplanets since becoming operational in 2022. But the sub-Neptune category, the ones most relevant to habitability questions, remains the hardest. The signal is incredibly faint. K2-18b required multiple transit observations stacked together to get a clear reading. Each transit gives you a slightly better picture, like increasing the exposure time on a camera.
And we're still in the early years of JWST. What comes next?
More observations of K2-18b are planned to settle the DM's question and pin down the atmospheric composition more precisely, but the real game changer will be looking at truly rocky planets in habitable zones. Planets like the TRAPPIST-1 system, which has 7 Earth-sized planets, 3 in the habitable zone. JWST is already studying those, though. Detecting atmospheres on Earth-sized planets is significantly harder than on larger sub-Neptunes.
Because smaller planets have thinner atmospheres?
thinner atmospheres and less surface area to filter starlight through. The signal gets proportionally weaker for TRAPPIST-1 planets. It might take years of accumulated data to confirm or deny the presence of an atmosphere, but that's the beauty of JWST. It was built to last at least 20 years. Time is on its side.
What would it take for scientists to go from possible water to confirmed habitable?
You'd need multiple independent lines of evidence: confirmed water vapor in the atmosphere, temperature measurements consistent with liquid water, the absence of atmospheric features that would rule out surface conditions suitable for life, and ideally a biosignature gas like oxygen or DMS that can't be easily explained by non-biological chemistry. We're not there yet for any planet, but 2 years ago we couldn't even detect molecules in a sub-Neptune's atmosphere. The pace of progress is staggering.
We went from we don't even know if exoplanets have atmospheres to we're debating whether this one has an ocean in about 2 years.
And in 2 more years, we might be having a very different conversation. Sources and papers are all linked below.